Hello. Today we are going to do problems from weekly contest 340. The first problem, prime and diagonal. So basically here we have zero indexed two-dimensional array, and we want to return the largest prime that exists in at least one of the diagonals of this 2D array or matrix, right? And if there is no prime in there, then we want to just return zero, right? And so pretty much if you take a look, for example, at this here, 11 is the largest prime that is in the diagonal at this position. Now the numbers can go up to 300, so not too big, which tells us that we should be able to solve it easily. And then the values can go up to 10 to the power of 6. So how do we tackle it? Okay, so how do we tackle this? Well, diagonals, it's easy to find, right? We just take I, and the one diagonal is all the values that have the same index. The other diagonal on the reverse side is just I rows minus I minus 1. That's the problem tells us that already. So what we need is just to know how can we check if these numbers are a prime. If they are prime, just keep track of the max, right? And just take the max against this and against this. But we want to take the max only if it's if this one is a prime and or this one is a prime, right? Because we want to find the largest prime that is in the diagonal, and these are the diagonal, and since we want the largest prime, we want to check if they are prime first. Now, how do we check if they are prime? Well, the easiest way is just to use some pre-processing to find all the primes up to the max element in the matrix, right? And then from there, we can just traverse the diagonals and just check if they are prime or not. And the easiest way to pre-process all the primes is just to use sieve of Eratosthenes. And the way to do that is I will do a short explanation, but feel free to look it up or check my other videos that have similar problems on primes. But the idea is the gist of the idea is first you have all the numbers, so 0 as indices, right, in an array. So number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this array will just have true if the number is prime and false otherwise. Now we know that 0 and 1 are not prime, so we put false, and then we start from 2, okay? And if first we check if the number is prime, right? So if the number is prime, then we want to mark all the multiples of it, right? All the numbers that are multiple of it as not prime, because by definition they are multiple of it, which means they are divisible by that number, which means they are not prime, because a prime number has no positive divisors other than 1 and itself, right? And so for 2, all the multiple of 4 are not primes because they are divisible by 2. So that's the idea. So we start from 2. And we start also, because otherwise we'll have just false. We start with all the elements are true. First, all the elements are marked as true, and then we'll mark them as false if we find that they are multiple of another number, right? So all of them start out as true. And then we put false for 0 and 1 because we know those are not prime. And now for 2. 2 because there was nothing before that is a multiple that when we multiply that 2 is a multiple of. And so 2 remains true. But when we get to 2 and it's true, we want to mark as false all those that 2 divides. So 4 is 2 multiplied by 2, right? So because 4 is a multiple of 2, we want to mark it as false. Let me actually just use a different color. So false. What's another multiple of 2? 6, 2 multiplied by 3, that's 6, so mark it as false. What's another one? 8, 4 multiplied by 2, that's 8, so false. And you get the idea. And now we do it for all of them all the way to the max of A. in this case, we can do it to the max of the matrix, or you could do it to the even 10 to the power of 9, like the highest number possible, okay? And then we go to 3, where 3 is true. So it's a prime, so we need to mark as the multiples of 3 as not prime, because 3 divides them. So 9 becomes false, and then other numbers 15 all the way down become false. And then 4 is already not prime, so we skip it, right? And then we go to, because that means we also marked multiples of 4 already. We marked them as not prime from the previous element, which is 2. And then 5 is prime, and so we mark all the multiples of 5 as not prime. So for example, 10 here, we will mark it as false, and you get the idea. We'll keep going. At the end, we will have, once we are done, we will have all the numbers that are prime, then the value would be true. Those that are not prime, the value would be false. Okay, so now that we have the is prime, we can just go to our matrix and then go for all the I values in the range of course, rows. And then we check if the element is prime, we take the max so far between it and the max so far. And if this one is prime, by just checking this prime array, if this one is prime, we also take the max of it, and that's pretty much it, right? And so the calculation for this one is going to be O of the max of A, because we'll go up to the max. And then for this one is going to be just the number of rows, right? So O of number of rows. And so the overall time, number of rows plus max of A. So it should be fast, or at least it should be within the time limit. Now in terms of space, we are using this extra array, which also is of max of A. And that's pretty much it, space. Yeah, so now let's just code this up and make sure it passes our test cases. Okay, so now let's code the solution that we saw in the overview. So first, we want to get the max of all the numbers in the matrix. So let's actually just mark this as A to make it easier. And so we just take the max of each row and then take the max of all of them. So for row in A, okay? And now we want to do sieve of Eratosthenes, which means we have this array of which marks whether a number is prime or not. And so initially we mark them all as true. This is for all up to M, the max value. Now we said we mark 0 and 1 as not prime, right? So these will be marked off as false. And then for X, we will start from 2 all the way to the end. And then we will check if X is prime, then we want to mark all the multiples of X as not prime. So let's call them Y, and we'll start from to the power of 2 all the way to the end, because we don't need past the max of the matrix, right? So each time we'll increment by X because we only want the multiples of X, right? And so we will mark them as not prime because they are divisible by X, right? So Y is not prime because it's divisible by X. Okay, Y is divisible by X by definition of the for loop that we defined here, okay? And now it's pretty easy. We have all the primes. So we start the problem says if there is no prime in the diagonal, we want to return 0. So we start out with 0 then. And then we take the max if we find a better number. So first we need just the length of the number of rows. Let's just call it the length of A. And then we go for each index, right? The diagonals are at the same index. That's what the problem says here already. And then the other one is I, and then the length, which is the number of rows, minus I minus 1. So we want to just check first that they are prime, right? If it's prime, we want to check if it's the max so far. And so we just say best is equal to the max of best and that number. Similarly here, if it's a prime, we also take the max. Because remember, we want just the largest in the diagonals. And so this would be rows minus I minus 1, and then we want to return the best one. Okay? And that should be it, really. So let's run it. Let's run it and make sure it passes. So this is for, let's actually just write it like this, multiplied by m plus 1. And sorry, this is not an array. This is actually like this, and this can be just like that. Okay. Okay, looks good. Let's submit. And this passes our test cases. Okay. Yeah, pretty straightforward solution. That's pretty much it. Please like and subscribe, and see you on the next one. Bye.